The last video was about deriving this equation right here. And one of the comments I made was that you end up with a parabola. You end up with a parabola here. Let's take a moment and just verify that yes, you do get a parabola. So copying this down, I'm going to break it into separate x and y components. So x is equal to v naught cosine alpha times t. Y is equal to v naught sine alpha times t minus 1/2 gt squared. And let me just emphasize, that's not cosine of alpha t. That's cosine alpha times t. That's sine alpha times t. We can solve for t in terms of x here, and then substitute in t in terms of x into our y equation to get y in terms of x. What do we end up with? T in terms of x would give us x divided by v naught cosine alpha. And so we plug in, everywhere we see a t over here, we place it with x over v naught cosine alpha. Y is v naught sine alpha times t is x over v naught cosine alpha minus 1/2 g times t squared. T squared will be x squared over v naught squared cosine alpha squared. And I think a couple things should cancel here. Those v naughts will cancel. Y will equal negative 1/2 g over v naught squared cosine squared alpha. All of that times x squared plus x times sine alpha over cosine alpha is tangent alpha. Tangent alpha times x. So here we see y is equal to negative 1/2 g over v naught squared cosine squared alpha times x squared plus tangent alpha times x. And in a particular fixed example, g is always constant, we're assuming, gravitational constant. V naught is constant in our example. Cosine, alpha is constant, so cosine square alpha will be constant. Tangent theta will be constant. So this is constant times x squared plus constant times x. This is a quadratic. This is a parabola. Okay, so that just goes to show that yes, you do get this kind of parabola here. Okay, let's do a more computational example. Let's, with actual numbers here, let's take a look. So projectile is fired from the origin over horizontal ground, an initial speed of 500 meters per second, and a launch angle of 60 degrees. Where will the projectile be 10 seconds later? So this fits into all of the things that we want it to fit. We're starting from the origin, that's great. We're given the initial speed and the launch angle. So that says v naught is equal to, and no vector sign here because this is speed, 500 meters per second, and alpha is 60 degrees. So we plop in all of this stuff in here to our RFT formula. We end up with RFT is 500 times, I'm just going to drop the units here. We'll put them back in at the end. 500 times cosine of 60 degrees, t I hat, plus 500 times sine of 60 degrees, t minus 1/2 times gt squared. And we'll be using g is 9.8 meters per second squared. That's a pretty darn good approximation. So negative 1/2 times 9.8 t squared times j hat. Okay, let's crunch this out. Cosine 60 degrees, cosine of pi over 3 radians. This is going to be 1/2. Sine of 60 degrees will be root 3 over 2. And so r of t ends up as, this ends up as 250 t I hat plus 250 square root 3 t minus 4.9 t squared times j hat. And to finish off this problem, where we'll be 10 seconds later, so this is asking for position when t is equal to 10, and so this is 2500 I hat, 250 times 10 is 2500, I hat plus 2500 square root 3 minus 4.9, 10 squared is 100, so minus 490 j hat, and approximately 250 I hat. I'm doing approximation here so I can get rid of that square root, plus 3840 j hat. So 10 seconds after we've launched, we've gone 2,500 meters horizontally. And as I noted in the previous video, the initial horizontal speed was 250, so 10 seconds, we've gone 2,500 meters, and then we are still 3,840 meters above the ground. Okay, so that is an example here of using these kind of equations. Something else that is worth going on here, something else that's worth talking about is, from this we can come up, what are some things about the motion that we can talk about? We can talk about what is the maximum height. That's one thing that we could wonder about. We could wonder, and then this is where it lands, assuming that we're on flat ground. This is where it lands. And so we can talk about range. And we can also talk about flight time. How long does it take for it to hit the ground? And so it turns out there's formulas. I'm not going to derive them, but here, height, flight time, or range for ideal projectile motion. In our ideal situation, the max height, y sub max, is given by v naught sine alpha squared divided by 2g. The flight time is given by t is 2v naught sine alpha over g, and the range is given, r is v naught squared over g times sine of 2 alpha. So I'm not going to do this, but we could go back to this problem. We have v naught, we have alpha. We could plug in v naught and alpha from this problem to figure out, what is the maximum height of this projectile. We could plug in, v naught and alpha into this equation to figure out when it's going to land. We can plug in v naught and alpha into this equation to figure out, how far away it's going to land. So very useful formulas here.